Good morning, good afternoon, good evening, everyone, those who have joined this session on IBPSA Webinar Series. Today we have Professor Morrison from Carleton University. He has already offered one webinar based on the keynote address which he provided in the UK last year. And today, this ninth session, he will be talking about a micro-cogeneration system performance prediction based on the book chapter. Thanks, Ian, for offering the second webinar on the platform. Over to you.
Okay, thank you, Rajan. Thank you for organizing this webinar series. I think it's a great initiative of IBPSA's. What I'd like to present today is the material covered in Chapter 12 of the book Building Performance Simulation for Design and Optimization. And it's quite a specialized topic, but what I'd like to do is give you a flavor for the techniques that are available for predicting the performance of micro-cogeneration devices. So for starters, what is micro-cogeneration? It is a form of cogeneration or combined heat and power where we're taking a single fuel source, typically natural gas, but not necessarily natural gas, and converting that to heat and electricity within the building site. And cogeneration exists on many different scales, from large-scale systems down to the micro-scale systems. Typically, the term micro-cogeneration applies to systems of electrical power outputs less than 15 kilowatts. Systems that are typically small enough to be placed within a residential building, a single-family house, or a small multifamily building. So why would one consider a micro-cogeneration device for providing heat and power to a residential building? Well, the technology does offer a number of potentials, and the word potential is important here. This is why we need simulation to be able to predict what the true performance will be. But there is potential for energy savings, reducing greenhouse gas emissions, and alleviating some congestion issues on the electrical grid. So there are lots of possibilities and potentials. Really what it relates to is scaling a power plant down to a very small scale and locating it at the point of thermal and electrical demand. So typically our electrical systems are composed of large generating stations, such as the one illustrated here, that are producing electrical power in relatively remote locations, and that's transported to demand sites. So this is a gas-fired system. In this case, it's located in the Netherlands, but these systems look pretty much the same throughout the world. We take the fuel source, natural gas in this case, and we combust it and take the thermal output, and through some kind of thermodynamic cycle, a heat engine, a Brayton cycle or a Rankine cycle typically, or some combined cycle, try to convert as much of that thermal energy as possible into mechanical energy, and then eventually to electrical energy, and then it's transmitted to the building site. But as you can see on this image here, there's two large cooling towers at this power generation station, and that's where the waste heat is rejected. So the goal of the cycle design is to convert as much of the thermal energy as possible to electricity. However, the laws of thermodynamics being what they are, we know we can't convert 100% of that thermal energy to electrical power. There will be some rejection of heat to the environment. So in this case, cooling towers are used to reject heat to the environment, and anywhere between 45 and up to 70% of the thermal energy produced through the combustion process is rejected to the environment in the form of waste heat. So that is energy that's lost. If we could scale the system down and place it within the building, then we have potential of, rather than throwing that heat away, is capturing it and using it to respond to the building's thermal demands. So with conventional electrical system topologies, we have the large generating stations operating in fairly remote locations. They're producing electrical energy. It's boosted up to high voltages and then transmitted over a high voltage system, transmission system, and then step down in voltages until we reach the load sites. In the case here, we're talking about load sites that are buildings, and we then have low voltage power that we use at the building site. But there's a large distance between the power plant location and the building site, so there's no opportunity to use that thermal output from the power plants typically to supply building thermal loads. So we have the potential, if we scale that system down, put it in the building, we have the potential to use the electrical energy, yes, but then also to capture and use the thermal energy output. And this is why there is an interest in micro-cogeneration. Potentially we could use much more of the energy that's liberated through the combustion of the fuel to supply the energy needs of the building. But there are certainly challenges in doing that. Rajan, I'm hearing some background voices. I don't know if the mute has gone off on some of the. Okay.
No, all the attendees are on mute. I'm just trying to check. Even I'm on mute, so you carry on. I'll figure it out. What's
okay. So there certainly are challenges, though. If we scale the system down, yes, we're producing the thermal output at the building site, but there are challenges in using that thermal output because of the temporal mismatch we have between electrical demands and thermal demands. So this graph is illustrating what thermal demands and electrical demands could look like in a typical residence over the course of one day. And we can see there are times of the day where we have very large electrical demands, typically in the morning and late afternoon, evening time, we have large electrical demands. And those periods of large electrical demands may not coincide to large thermal demands. There are other periods where we have lots of thermal demands overnight for space heating, water heating, but very little electrical demand. So it means that if we place the micro-cogeneration system within the building, it will be producing heat and electricity concurrently, but the demands for heat and electricity aren't concurrent. So invariably this necessitates some kind it's producing heat and electricity within the building, but we also have interactions with the electrical grid. The thermal output from the cogeneration system could interact with a thermal storage within the building, and that thermal energy storage interacts now with space heating and domestic hot water systems. So the behavior of the occupants in the building when they demand electricity, when they demand hot water, will influence the performance. The weather conditions will influence the performance. The building characteristics will influence performance. The electrical grid will influence performance. How we dispatch the micro-cogen system. Do we respond to thermal needs or electrical needs, or do we respond to what's happening on the electrical grid? All of these factors influence the overall performance of the system. And therefore, in order to accurately predict how such a system might perform and whether or not it will reduce energy consumption and reduce greenhouse gas emissions, requires us to consider all of these things concurrently. And that's where building performance simulation offers us that possibility, because we can simulate the behavior of all of these subdomains within BPS. But in order to do so, we need appropriate models to represent the performance of micro-cogen systems, because historically those types of models haven't been available in BPS. So we'll talk about the models that are available now, but first a quick review of some of the types of micro-cogeneration devices, or prime movers as they're sometimes called, that are available. This is an illustration of a system that's been marketed in Japan for a number of years. Well over 80,000 units of this particular Honda system have been installed in Japan. Typically outdoor installations where the prime mover is an internal combustion engine. So this is a reciprocating piston type heat engine that's going to produce the mechanical energy from the combustion of the natural gas and then produce electrical energy, and it interacts with a thermal storage tank. And then the system is interacting with the electrical grid. This system is sized at about 1 kilowatt electrical output, close to 3 kilowatts of thermal output, and has a combined efficiency of about 85%, meaning that perhaps about 30 to 35% of the fuel's energy release can be converted to electricity, and another 50% or so can be converted to thermal energy. So if we can configure the system to use all of that energy, we have a combined efficiency of 85%, which is far higher than can be achieved with a central power plant that's not exploiting the waste heat. So these are internal combustion engines, quite common. Another combustion technology that's also been developed at the micro scale are Stirling engines. These are external combustion devices that use a heat engine essentially to convert that thermal energy to electricity. They tend to have much lower electrical conversion efficiencies than the internal combustion engines and higher thermal output, so the heat to power ratio is quite different than an internal combustion engine. There's a number of companies that have produced such devices, but really this technology hasn't taken off to the same extent as the internal combustion engines, which are a more mature technology, let's say. The other class of devices are fuel cell based, where it's not a combustion device at all. There's an electrochemical reaction to convert the energy contained in the fuel, often natural gas, but other fuel sources can be used, such as hydrogen, but natural gas is the most common. So an electrical chemical reaction to convert that energy in the fuel into electricity, and it also produces thermal energy. These have electrical conversion efficiencies that are similar or a little bit higher than the internal combustion engine devices, and there's many tens of thousands of such units that have been installed. And again, Japan is really the leader in terms of the adoption of micro-cogeneration technologies, thanks to very ambitious government programs in the past years. So this picture here illustrates one type of fuel cell that's commonly used, the most commonly used for micro-cogen, which is the proton exchange membrane type fuel cells. These operate at relatively low temperatures, 60 to 80 degrees. But there's another fuel cell technology, solid oxide fuel cells, that operate at much higher temperatures, 800 degrees or higher, that are also used in cogeneration. So although they're both fuel cells, they have very, very different chemistries and very different system arrangements. So we have a number of different prime movers for the micro-cogeneration devices. So there's certainly a need to have models that can represent their behavior that can be embedded into simulation programs. So what these cogeneration devices look like on the inside is, it really depends greatly on the system manufacturer and the prime mover technology. But here's a schematic representation of what a solid oxide fuel cell system could look like. So there are many subcomponents that are handling the air and the fuel streams. And we have a number of heat exchangers internally that are preparing the fuel and the air for direct injection into the fuel cell itself. So this would represent the anode, electrolyte, and cathode of the fuel cell, which is really just one component of this overall system. There's likely an afterburner where unreacted fuel is combusted, and then heat exchangers to try to recover the thermal energy and transfer it into a useful form that can be applied within the buildings. So typically these are water-based systems where we have a cold water stream coming into some heat exchanger, and then it's recovering thermal energy from the fuel cell and then producing a hot water stream that can connect to the rest of the building's plant system. So that might be a hot water storage tank that's connected to hot water radiators within the building that supply domestic hot water. We also have ancillary electrical devices for power conditioning, for converting the direct current that's produced by the fuel cell into AC current, and then it can connect then to the electrical grid. And the arrangement of these components varies from manufacturer to manufacturer, and certainly we would have a different arrangement of components for a proton exchange membrane fuel cell, a different arrangement of components for an internal combustion engine and Stirling engines. So in terms of how do we develop models to represent these devices so that we can use them within building simulation programs, there's really a substantial difference in the way fuel cell systems versus the combustion systems are designed and operated. So it's appropriate to have separate models for these two main classes of technologies. So some work was done through two IEA Energy Conservation in Buildings research annexes, Annex 42 and Annex 54, on the development of models for these cogeneration devices that could be implanted into building simulation programs. So what I'm going to show here is the topology of these models that were developed by these research annexes. The first one is a model that's appropriate for fuel cell micro-cogeneration devices. And this model has been structured so that it can represent the behavior of either a solid oxide fuel cell, the high temperature type fuel cells, or the proton exchange membrane low temperature fuel cells. And it has a number of subsystems or control volumes that represent major energy conversion devices. And the way the model is structured is each one of these control volumes or subsystems is represented by energy and mass balances internally. So energy and mass balances are formed on each of these subsystems, and then a set of equations is concurrently solved to estimate the performance of the complete system. So we have control volumes that represent, for example, the blower that brings air into the device, into the fuel cell power module. And this fuel cell power module will include the fuel cell stack, but a number of ancillary components as well. But it's treated as a control volume, so we have streams of air and fuel and potentially liquid water flowing into that control volume. And that control volume is producing electricity, DC current, over here, and it's also producing potentially a stream of hot water or a stream of hot gas. And the stream of hot water, which would typically be the case with a PEM fuel cell, passes through a heat exchanger that can then communicate with the building plant. If it's a solid oxide fuel cell, it's probably producing a stream of hot gas, and it would come down through, hot gas coming through here, going through an auxiliary burner, and then through a heat recovery device that would interact with the building plant. So by having a generalized model like this, individual control volumes can be turned on or off to represent a particular technology. And within the simulation models, energy and mass balances have to be performed and calculated for each one of these control volumes. So we'll just focus now on the control volume. As an example, there's a control volume representing this gas to water heat exchanger. So this is the device that's taking the hot product gases that come off the fuel cell stack, pass through an auxiliary burner, and then into this heat exchanger. And this heat exchanger's job is to extract as much of that thermal energy as possible to transfer to a water stream that connects to the building's plant. So there's a blown up view of that heat exchanger. We have hot gases coming in, cooled gases exiting, cold water in, and then hot water out. And we're trying to simulate now the performance of that heat exchanger. So in this model that was developed in these IEA annexes, it treats this device as a steady state heat transfer process, and it models the heat transfer from the gas to the water using a log mean temperature difference approach with the UA value for the heat exchanger. So the user has to somehow provide information that characterizes that heat exchanger device with a UA value. And then the four temperatures that are entering and exiting, of the streams entering and exiting the heat exchanger, are represented in the log mean temperature difference. And we can also write that as, because it's a steady state assumption and we're assuming no parasitic heat losses from the heat exchanger, we can represent that as also equal to the heat extracted from the gas stream is also equal to the heat added to the water stream. So under these set of assumptions, we can write a set of equations now that relate the characteristics of the heat exchanger, the UA value, the flow rate of gas and water through the heat exchanger, and then the temperatures entering and leaving the heat exchanger. And when we rearrange that set of equations, we can now write a simulation equation that calculates the temperature of the gases, cooled gases exiting the heat exchanger as some function of the temperature of the hot gas coming in and the water coming in. And then the parameters in this equation include the flow rates of the gas and water streams, as well as this UA value that the user has to somehow characterize. So we now have a simulation equation that will calculate the temperature leaving as a function of temperatures entering. And the equations representing the other control volumes in the system will have similar equations that will calculate the temperature of the gas entering and the temperature of the water entering. So we end up with a matrix of interrelated equations that are coupled together that have to be solved either concurrently or iteratively, depending upon how the simulation program is structured. But we can now, by solving that entire set of equations, determine the operational state of the fuel cell and all these internal temperatures at any given time step in a simulation. But in order to do that, the user does have to provide some information. So for example, this UA value characterizing the heat exchanger in this case has to be described by the user. So the model uses a parametric form to represent this UA value. And this UA value is cast in a functional form that relates it to the flow rates of water. N dot W is the flow rate of water, and N dot G is the flow rate of gas through that heat exchanger. And it has a number of empirical constants. These H values in the equation are empirical constants. And this is what the user has to provide the model, these empirical constants. And they can only come from, they're empiric in nature, they can only come from the testing of a system. So in order to exercise a model like this, we need to have a device that can be tested, that can be configured with instrumentation and tested to provide enough data. So in this case, an experiment was run on a solid oxide fuel cell, producing the red data points here that shows how the UA coefficient can be derived from those measured data, how that varies as a function of water flow rate, and how that UA value varies as a function of gas flow rate. And then using those data, this equation can be regressed to determine the values of these empirical coefficients. So in order to exercise a model like this, we need to run a series of experiments, produce such coefficients. And there are published data available on particular micro-cogeneration fuel cell systems that provide these coefficients that the user would need. So that's the general structure of the fuel cell model. A very different approach is used in modeling the combustion devices, the internal combustion engines and the Stirling engine devices. With these devices, they typically they're very often heat-led devices. So they're cycling on and off much more rapidly than the fuel cell devices would be. And they're also thermally more massive. So as a result, the transient behavior of these devices is very important. Consequently, the modeling approach is very different in that the thermal mass of heat exchangers internal to these devices are considered in the model. So in the case of calculating the thermal efficiency of the internal combustion engine or Stirling engine device, an equation is written that represents the energy balance here, and in this case transient terms appear in this energy balance where the thermal response of the engine becomes important in the energy balance. The thermal response of the heat exchanger that transfers the thermal energy out of the engine also becomes important. And also there's a heat loss term that represents parasitic heat losses to the room or the space containing the engine. So a very different modeling approach. But again, it is empirical in nature, and the user has to supply data to characterize, in this case, the efficiency, the thermal efficiency of this device at steady state conditions. So that's what eta TH represents in this case. And again, a parametric type form of equation is used where that efficiency, the thermal efficiency, is some functional form of the flow rate of the fuel through the device, as well as the mass flow rate of the water through the heat recovery water and the temperature of the water coming in. So this is some parametric equation that was found to well represent the behavior of many devices, but the job now is to establish these empirical coefficients, these eta values in this equation. These are the empirical inputs that must be provided by the user. So again, some testing has been performed on some of these devices, and these empirical coefficients are available on a limited set of devices. So to illustrate how this can be used, to getting back to what we talked about at the very start, if we want to estimate how this complete energy system performs, the cogeneration system plus thermal storage plus perhaps electrical storage plus interaction with the building's heating system, supplying domestic hot water, we can put all of this together now in a building simulation program and simulate the performance of each one of these domains. So what I'm going to show you here is a simple example where we have a solid oxide fuel cell cogeneration device inside this box that is producing heat and electricity from natural gas, and it's coupled to the building's heating system through a water loop. So we circulate water from a water tank through the cogeneration system to pick up the thermal output, and that heats up the tank, and the tank has a supplementary burner if necessary, and this tank now can supply, through a water-to-air heat exchanger, can supply the space heating needs of the house. So return air from the house is passed through this heat exchanger, warmed up, and then sent to the house to supply space heating needs. So this is a situation that we're simulating here now. To represent this, the model that I just showed you for the fuel cell system is implemented in a building simulation tool, and then models representing storage tanks, pumps, heat exchangers, fans, etc. are all implemented, and models representing the building's thermal performance are implemented. So here's an example of the kinds of results that now can be produced with this fuel cell model integrated into the building simulation program. These are results integrated monthly over a year, where it's showing the hollow red rectangles here representing the electrical production of the fuel cell unit. And this is a particular operating scenario where the fuel cell is producing 1 kilowatt of electrical output continuously. And it's producing that electrical output, but that electrical output of 1 kilowatt is not always sufficient to meet the building's electrical needs, so there is some grid import, which is shown in the solid red line here. So we're pulling some energy from the grid, electrical grid as well, to meet demands where that exceed 1 kilowatt. But there are also times when 1 kilowatt of electrical output is too much for the building's needs, so we're exporting to the electrical grid, and that's shown down here by the blue bars. So with this type of model, we're now able to predict how this building would have to integrate with the electrical grid. These are the monthly integrated results from a thermal perspective. So it's showing you here that the solid or the hollow red boxes here are the thermal output from the cogeneration devices, and then the space heating needs of the house are shown down here, and this is showing that in the month of January, for example, the space heating needs of the building are much greater than the thermal output from the fuel cell, and in that case the auxiliary burner in the tank has to cycle on. And then there's a small blue bar under here that's showing, well, even though over a monthly basis the thermal output was insufficient to meet the building's thermal needs, there were certain times when the thermal output exceeded the building's thermal needs and exceeded the tank's capacity to store that energy, so we had to throw some of that energy away. So these are the bars down here, and those bars are obviously larger in the summertime. So without simulating the performance of such a system on a time step basis, we wouldn't be able to necessarily capture that level of information. And now with the simulation tool, we can also compare how this device would perform with different control strategies, different dispatch strategies. So the results I just showed you now were operating this device at a constant 1 kilowatt electrical output. But another operating scenario is to have the device follow the building's electrical demands. And we have a very different set of results in terms of electrical output and useful thermal output and efficiency of the overall efficiency device, and certainly the amount of interaction with the electrical grid varies greatly between these operating scenarios. And then we can also look at a different operating scenario where we thermally load follow. And again, we have a very different set of performance predictions. So by characterizing a detailed model like this and then representing it in building simulation, we can have a good estimate of how this system would perform, and it allows us to perform a number of what-if analyses, looking at different control strategies, maybe changing the size of the thermal storage, maybe changing the behavior of the occupants in terms of electrical demand patterns. And that's the power of representing such a thing in building simulation. So that's a very quick tour through how these models are structured. And if any of you are interested in learning more, there's quite a bit of detail in this chapter of the book. And the models, as I've described here and are described in greater detail in the book, are available in 3 commonly used building simulation tools: Energy Plus, ESPR, and Transys. And there's many more details provided in the final reports of these 2 IEA annexes that I mentioned, 42 and 54. And it's not trivial to use these models, for sure. They're fairly complex models. To aid people to learn how to apply these models within their simulation tools, the book chapter also includes a series of assignments that start off with a very, very simple case where the user will configure their tool, and again, they can use Energy Plus, ESPR, or Transys to represent a simple fuel cell cogeneration device that's simulated, its behavior is simulated on its own. So that's the first step. And then after the user has accomplished that, they go on to the next step where they can take some calibration data that comes from measurements and learn how to develop the inputs for their simulation tool. And then they can apply dispatch strategies, and then they can put that cogeneration system together with devices that represent thermal storage tanks and pumps and heat exchangers and radiant floor systems, whatever they like, to now model the behavior of a complete energy system. So with that, I'm happy to take any questions that you might have.
Thank you, Ian. We have one question so far, and in fact 2, and the person has requested that that I should narrate that. This question is from Harshul Singhal. Question is there any documentation to understand the efficiency curves or get the values for different microturbine in case someone needs to model such system in the building? Especially for fuel cells, PNNL's Advanced Guide 25130 doesn't have any information on it for some standard curves. Do you want me to repeat question, Ian,
No,
or
no.
is it fine? Yeah, okay.
No, that's okay. So yes, a good question. These models are empiric in nature, so in order to use these models, we need to have some measured data from cogeneration devices. Now, work was done within these 2 IEA annexes to characterize some solid oxide fuel cell, PEM fuel cell, internal combustion engine, and Stirling engine devices. And the performance data, or performance curves if you like, for these specific products are available through publications. So if you go to the Annex 42 and Annex 54 final reports, you can find that information there. In an ideal world, we would have data available on many more devices, but it's a fairly laborious effort to conduct the experiments with sufficient level of accuracy to develop these performance curves, and the manufacturers generally are not motivated to go through that level of effort. So there are many products on the market for which unfortunately we don't have the detailed performance curves that are necessary. What often happens is the manufacturers will quote the performance under a specific operating condition. And that's generally not terribly useful for estimating how it's going to perform in a dynamic situation when it's interacting with the building.
Okay, thanks. Do we have any other question from audience? I'm not seeing anything on the panel right now. Any question from anyone? Okay, seems we are not getting any other queries on this. With that note, I again wish to thank Jan for offering this webinar. And this webinar would be available in a YouTube channel of IBPSA University. Those who wish to refer later on or refer to your friends, you can do that. And also, I encourage people to register for BS 2017, which is planned in San Francisco in the first week of August. Please visit website and do register for conference. Thanks, Jan, for webinar again. And with this, I'm ending webinar this time. Thank you.
Okay, thank you, Rajan.